Okay, we're going to take a look at composite functions. And a composite function is the idea of one function within another one. So to get like a real definition of them, the first thing we have to do is kind of understand these two things here. Both of these are functions. In fact, you can put them through a vertical line test on a graph, and you can prove that idea. But we're just going to take their word for it, that they've given us two functions, and they're written in function notation. And function notation is just like the name of the function. So, for instance, they use f just because they tend to be called functions, and f at x. X is the variable within that function. They give this one the letter G just because it comes after F in the alphabet, but you could name it anything you like. But it also uses the variable X in here. Oh, you're welcome. So the first one here deals with composite function, and that's the idea of one function within another one. So you can tackle a question like this in multiple ways. One of the ways that we'll do it is what we'll do is we'll break them apart and then use the output of one as the input to the other, or we can put them together as a single function. So the first way we're going to try this is we have two functions. One's called g at x and one is f at x. Okay. All this is saying is they want you to find g at x. Oops, I should have done that in blue since I highlighted it that way. They want you to find g at x when the variable is 3. Whatever the output to that is, okay, we'll call that the output. They want that to then be the input to the function f at x. Okay, so in other words, you're solving one, then taking that value, plug it into the next, and then finding what the output to that is. And they use this term as a, well, that's not how you spell output and input, kind of because it relates to computer science, but functions is the same concept. So you can tackle this by breaking them apart. The very internal part says here, g at 3. So we'll start with that. We have the function g at x is equal to x squared. Okay, that's cute. What we want to do is replace this x value with that number 3. When you do that, whatever variable is in the rest of the function on the right-hand side, we replace that with whatever we're substituting in for the variable on the left side of the function notation. So in this case, it's 3. 3 happens to be squared. We carry that out, and we end up with the value of 9. So the output to g at 3 is 9. Well, because this is a composite function, essentially what we've done is we took the original, okay, and what we've just done is we have now got a value for it. That value is now 9. So the idea is that is dropped off, and now we're just left with f at 9. So same idea, I'm going to go take a look at what the f function is. So we'll say f at x is equal to x plus 2. We're substituting in the number 9 for the x value. So whatever it occurs on the right-hand side of this equation, we replace it with the number 9. So 9 plus 2, and we end up with 11. Okay. So while it looks like we've carried out two different calculations here, truly what we got of an answer is actually the answer to the f at g at 3. Okay. I don't know if they can't remember if they use square brackets or not, is equal to the value of 11. So we broke that into two pieces. Okay. We're going to tackle the second one, but I'm going to attempt it in a different manner just to show you that it can be done in two ways. First, we'll read this one. What did I use? Green for f? Okay. So the first one, if we do it the first way, I would just plug in -8 into f, get a value, and then plug that into g. The other way I can look at that is this is a function in a function. So I'm going to rewrite the two of them. Our g was equal to x squared, and then our f was equal to x plus 2. X plus 2, and I forgot to put a bracket here on the g. Squeeze it in. Okay. What we actually can do, this one is asking for, and now before I walk away, what was it asking for? It was f in g. Okay. So they wanted g at f at -8. Okay. Instead of actually solving for the 8, what we can do is we can build a new function. We'll leave this as x. Okay. And really what that means is I'm going to plug in the function of f at x into the function g at x. Okay, so our g is the outermost function here. So I'm going to take g at x, and we know that that is equal to x squared. In our next step, I'm going to take f at x. Instead of confusing the notation, I'm going to take the right-hand side of f at x, and we're going to plug that in for the variable of g at x. So in other words, we get g at x plus 2. Okay, which means the x value in the equation, we're going to replace it with the exact same thing. So we set a bracket, we do some substitution, x plus 2 squared. Okay, so what we've just built now is a brand new function. You could give it a new name if you like, but it will give us the function that we can plug -8 into. So we're going to simplify the right-hand side. This is technically a quadratic, x plus 2, x plus 2. And if we quickly just use our distribution property, sometimes they call it FOIL, rainbow method, whatever it is, this becomes x squared plus 4x plus 4, okay? So g of f of x, okay, without putting any values, is actually equal to this. So instead of breaking it into 2, what I did is I built a new function. And now what I'm going to do is I'm going to take g at f at, I believe they asked for -8. Let me double check that. Yeah, they did. F at -8. Well, because we now have a new general function for this, which is our x squared plus 4x plus 4, we can replace each of the x's with the value for this function. So -8 squared plus 4 times -8 plus 4. And now we just carry this out. Becomes 64, subtract 32. Yep. Plus 4 becomes 32 plus 4, 36 should be our answer in this one. Okay, so what we just did there is 2 different ways of going about this. We're going to zoom back in to do one more. One of them, we decided to break it into 2 pieces. I figured out the inner part and said g at 3. I calculated g at 3, got a value. And then we knew the outer function was f, so we took that output, made it the input to the next function, and calculated. In our second version, they reversed the functions. Okay, I found a general solution. I created a general function here by not putting in any numbers, but instead plugging that in and getting a new general solution to it. The final one is actually that. It's the idea of this is a function within f within g. So I'm going to do this one step at a time, similar to the first one. This is the same idea. I could technically do it this way. It just might get a bit convoluted. So let's zoom back in. The very last one is g at f and 3x plus 4. So g at f at 3x plus 4. Okay. We just have to make sure we remember f at x is equal to x plus 2, and g at x is equal to x squared. Okay. So the inner part here, they are substituting in for that variable x. So we're going to place this variable with essentially an entire function. So we'll break it apart again. I'm going to do my f first. So we're going to say f at 3x plus 4 is equal to, we're going to replace that x with 3x plus 4. Then we're going to add 2. So the only thing that changed was the variable. The constant, that stays the same. And then we said about calculating it. These brackets can drop right off, and essentially I'm just going to add 4 and 2 here. So we get 3x plus 6. Okay. So that's the f at 3x plus 4. So we've now just solved this piece. But remember, that's all internally inside of g. So now we take this as the output, and we're going to plug it into our g at x function, which originally reads g at x is equal to x squared. Well, we're going to replace the x with that value. So we get g at 3x plus 6. And we replace that variable. We square it, which is going to be really similar to what we did over here. And now we're just actually going to get an equation. Because they can give us a number, so notice they didn't just give us a number here. They've left a variable. So in all likelihood, our final answer is going to have a variable. It's possible, like in certain scenarios, it cancels out. But in this one, it's not. We're going to end up with an equation as an answer to this. So we expand this one. I'll go through this part a little slower just because the numbers are a bit harder to work with. So if we use distributive, I do 3x times 3x, 3x times 6. That's 9x squared plus 18x. And then do 6 times 3x, 6 times 6, which is 18x plus 36. And we just collect the two like terms in the middle. We get 9x squared plus 36x plus 36. So that's kind of like a rundown of what a composite function is, along with figuring out like the function notation as part of it.